So it's a pleasure to be here. Thank you for inviting me. Thanks to the organizers, even the absent one, Vincent, who I don't know if he's going to come later in the week or any information. Probably not. Okay. So I'm going to tell you about some correspondence by Alde. Originally, it was developed by Alde, Gayotto, and Tachikawa 50 years ago. And there has been lots of developments throughout the years. I think most of the activity happened in the 2010s. Nowadays, it's broadened so much that it's harder to recognize what is still a consequence of that and what is sort of in the bigger picture of supersymmetric gauge theory and CFT. So I will take a point of view that's sort of stuck in time in 2015 or so, when I sort of started paying less attention to the field. But I think if people want to add comments to complete, telling me like, oh, this has been proven for by now, or whatever, they can interject without hesitation. So I have basically three goals, which are, set up the basics of AGT, which is going to be super boring to those who already know it, but hopefully understandable to everyone. Probably point you to, but this is immediate, to my review of AGT. So if you want more details, probably from 2020 or something like this, you can see there, and you can have infinitely many references, so I will not cite many papers here. And my ultimate goal is to talk a bit, if I manage to reach this point, about 6J symbols, about some 6J symbols of UQ, SLN, which are generalizations of what Jörg mentioned for SL2. So we'll see if we get to this point or not. So what is the AGT correspondence? At its core, it's, as I wrote in the title, a 2D CFT valued in 4D equals 2 theories. And the idea is that for each simply laced Liatra G, there is a six-dimensional theory, which I will try to give you some glimpse about, which maybe people are XG. And if you put this XG on a Riemann surface C with punctures, so just like you would put, for example, uveal CFT, a 2D CFT on a Riemann surface with punctures and compute correlators, here you can take the 6D theory, put it on a Riemann surface times some 4 manifold. And this is actually equivalent to a certain 4D symmetric theory, which is going to be called TG of this Riemann surface on the 4 manifold. And so this leads to lots of different avatars of the AGT correspondence depending on what 4 manifold you put. And of course, a lot of richness depending on what you do on the Riemann surface side. Okay, so the first step is going to be telling you about the 6D theory, then to explain the basic dictionary, and eventually specialize to M4 equals the 4 sphere, a squashed version of the 4 sphere, which gives you 2D CFT called TODA CFT, which is a generalization of uveal CFT. So this is going to connect 4D equals 2 theories on S4B to 2D CFT, to TODA CFT. Okay, so already I'm not in the same order I was planning, but that's fine. Let's talk about the 6D origin.
This is usual station.
Again?
I mean, this is very usual thing.
Yeah, I shouldn't worry about that. But, anyway, so what do I have to tell you about the 6D theory? So first of all, you have lots of supersymmetry algebras depending on the dimension and the number of supersymmetries, and lots of superconformal algebras. And here I'm going to look at the highest dimension, highest amount of supersymmetry, or superconformal symmetry. And the algebra is denoted OSP 8 star 4. You can think of it as some kind of super matrices, like 8 times 8, 4 times 4 pieces. This is bosonic. Same thing here. And here you have the supercharges, I guess Q, and S. The supercharges. And so this contains, well, it's these types of matrices with some reality property that's analogous to symmetry in the algebra SO. So this contains SO star 8, which is a real form of SO8, which is the conformal group, conformal algebra in 6D. And it contains USP 4, which is this the R symmetry of, also I want to say that it's the same as SO5. This is just an equality of the algebras. R symmetry, which acts on the supercharges. Okay, so once you have this algebra, you can start trying to make at least 3 theories.
You're not worried about the signature of Minkowski, it doesn't make a theory, right?
This is the one in Minkowski's signature, I believe, from memory.
It's star.
It's an annoying thing where, okay, I forget exactly, but it has, like it involves quaternions if you really want to sit down and...
So it's not SO 6, 2, it's not this.
No, okay, yes, I forgot to say, yes, thanks. This is actually isomorphic to SO6, 2. So the story really is, you want a superalgebra such that the off-diagonal pieces are spinor representations of the conformal...
So star means spinor. Star corresponds to spinor representation of SO.
So remember that SO8 has this triality symmetry? And like you can see this, the real form as being SO6, 2 or SO probably 2, 6 or this third SO star 8 in which such that, okay, it exchanges spinors and vectors and so on. So the story is annoying and I don't want to go too much in detail. The main thing is this R symmetry, which I'm going to use a little bit. So now you can start with making an abelian theory, which is going to be made of a single tensor, what is called a tensor multiplet. And this tensor multiplet consists of mu and u, which is a real self-dual 2 form. So self-dual just means dB equals star dB. This is our 3 forms in 6 dimensions. A bunch of real spinors in the 4-dimensional representation of R symmetry, and a bunch of real scalars, or 5 real scalars in the 5 of R symmetry. 5-dimensional representation of R symmetry. When you reduce this theory, so this is just a free theory. The action is very easy to write. When you reduce, it reduces to when you reduce on a circle, it gives you just a 1 form, a bunch of spinors and scalar fields, which are just 5D n equals to U1 superiorness. So far this is just complete trivialities. If you write down the Lagrangian, you sit down, decompose into KK modes, and you actually find this. The one non-trivial thing is that this super-Yang-Mills has gauge coupling, and that this gauge coupling is related to the radius of the circle which you're compactifying here, reducing. This will go up later on. No, now, can you make this non-abelian, which is really the interesting thing? The answer is, this condition is hard to generalize, contrarily to Yang-Mills, where you can write self-dual instantons. You can write f star f equals f, and you can do it with or without non-abelian, in the abelian or non-abelian case. Here you cannot, because there's no b wedge b or anything like this you can write. So the non-abelian case, what you do is to say, okay, in 5D, n equals 2, we know SUN super Yang-Mills. And actually you know it for any Lie algebra G, super Yang-Mills. And what happens is that when you look at excitations of this, so if you look at instanton particles, so you have just excitations of these a mu, lambda, and phi, but you also have instantons which have, which I don't know how much I should say about instantons, but I guess these are codimension 4 objects with non-trivial integral of f wedge f. So in 5 dimensions, you can really think of them as point-like in 4 of the dimensions, but extended in the 5th direction with a non-trivial, if you integrate on a given slice, f wedge f is going to be some number. So there's actually some quantization which I don't want to get into of this integral of f wedge f. But anyway, so you have these instantons which in 5 dimensions are particles, and the mass of these instantons is going to be 1 over d5d squared, which matches what you could expect for kk modes of some hypothetical 6D theory. On a circle of radius R5 equals G and Mills, sorry, G5D squared. So this is, it's tempting to say, and it's actually what we expect, that 5D equals 2 super Yang-Mills is equivalent to just, is a definition of the 6D theory I'm interested in, reduced on a circle. And if you want to decompactify, to get rid of the reduction on a circle, you want to take the radius to infinity, which is G5D to infinity, which is a strongly coupled limit. Of course, very difficult to analyze. So this is not a very helpful definition in full generality, but in some cases it's going to be enough to understand various reductions of your 6D theory to lower dimensional spaces. As soon as you have a circle, you know that this part of the story is going to be controlled by 5D n equals 2 super Yang-Mills. There are other constructions which from string theory, and one interesting one for us is in the case of SUN. What you can do is to look at, so the 5D n equals 2 SUN Yang-Mills, it's known that it's the world volume theory of n d4 branes, parallel d4 branes. These are 5-dimensional objects in string theory. Okay, modulo the center of mass, which I'm not going to care about at this point. And we know this is in type 2A strings. And we can lift this to n theory, basically because type 2A strings are just M theory on a circle. And so these n d4 branes are just n m5 branes on a circle, and you can get rid of the circle. So the theory on n m5 branes is, I mean, this is another way of defining the 6D theory, which I guess I called it X SUI. So there are different ways of getting to the idea that there should be some such theory. Nobody knows how to define it from first principles. There's no Lagrangian description, and it's not expected that there is any way of constructing it other than these sort of limits or abstract ways from string theory. Especially because, as we will see, when you reduce it, you get all sorts of crazy 4D n = 2 theories which have no nice descriptions anyway. So it would be surprising if this has a nice description, but then you reduce it, it stops having that. So this theory, okay, it's fine. It reduces to Yang-Mills in some reducible circle. But the other interesting thing is that vacua of this theory are labeled by the positions of let's say, let's call them phi 1, 2, 3, 4, 5. I, 1 to n, of the n m5 branes in the 5 transverse directions. So this is very analogous to looking at the Coulomb branch of Yang-Mills theories, gauge theories more generally. Here we're looking at what's called the tensor branch in 6th dimension, because you're giving a vacuum excitation value to these phis, which are in a tensor multiplet, scalars in a tensor multiplet. And near a vacuum, the infrared effective theory of fluctuations around this vacuum, it's just n-1 copies. The -1 is always because you have to be careful about the center of mass and it decouples from everything else. So it's n-1 copies of the abelian theory I mentioned. Okay. So that's sort of the low energy description, the vacua and low energy description. The other thing you need to know is that this theory has defects. And it has two types of, well, I should say, differently. It has half BPS. In other words, it has half BPS defect, sorry. In other words, extended operators that preserve half of the supersymmetry. You can construct them through various brane configurations. I'm going to skip over this. But the end point is that you have codimension 4 defects, which are so two-dimensional, so surface defects, which are analogs of Wilson lines. They're labeled by representations of the Lie algebra G, and you can think of them like in the IR description. They're going to be essentially sums over the weights in the given representation of exponential integral of b, I guess, well, weight w in the representation, and then it's this. So here you have a two form, you integrate it over the surface, that is the place where you put your operator, and you just pick one particular component of this piece. So these are really analogs of Wilson lines in gauge theories, but here extended to one dimension higher. So these are some important defects, and some other defects which are even more important for AGT, but harder to describe in such very down-to-earth manner, or could I mention two defects, which are labeled by NAM data, or in other words, maps, homomorphisms between from SU2 to the Lie algebra. And so for SUN, this is just a partition of n. And we'll see in much more detail why this happens. I don't have a very simple way of explaining how this shows up until a bit later in the lectures. These are essential. These are going to be the punctures of my Riemann surface. It's codimension 2. Punctures are codimension 2. Any questions so far?
I have a question. So here, your argument about the vector structure is in the limit g goes to infinity, more general than that.
So the g goes to infinity limit gives you the 6D theory on flat space.
Yeah.
In most cases, I will be caring about the theory reduced to a Riemann surface. And a Riemann surface can be made of lots of tubes, basically. So the idea is that this Yang-Mills is going to be a big building block of the lower dimensional theories I'm interested in.
I'm asking a simpler question. This argument holds for infinite G or finite G?
This classification?
No, the argument about the vacuum structure.
This you can... This is supposed to hold for the 6D theory. And you can sort of see it from the M theory description, which is just a genuine description of the 6D theory without any compactification. You can look at M theory in 11 dimensions and look at how the M5 branes fluctuate. Of course, none of that can be made rigorous in 6D, but the reduction to 5D is sort of better. I mean, it's not nearly as rigorous as what you would hope for, because you have no path-integral definition or whatever, but it's sort of rigorous in 5D, not really rigorous in 6D. Okay, so we have this 6D theory. It has lots of features. How do we extract 4D theories from it? Well, if you just naively put the 6D theory on a curved space, it's not going to preserve supersymmetry, any supersymmetry whatsoever. So you're going to get some crazy four-dimensional theories with lots of problems with renormalization and so on. So instead, what you do is a partial topological twist. And the idea is, when you want to couple a QFT to curved space, what you do is you deform your Lagrangian by a perturbation of the metric times the stress tensor. That's for usual QFTs, which are just trying to turn on the metric. But when you have a supersymmetric QFT, you can turn on background for the metric, but you can also turn on backgrounds for other components of the stress tensor, dual to the stress tensor multiplet. So you have the stress tensor describing translation symmetry. You have the supercurrents describing the supercharges, and you have R symmetry, the R symmetry current, and you can turn on backgrounds for all of them. And what we're going to do is pick a background where psi is just 0, no strange fermionic background, and A is, roughly speaking, a derivative of G, and G is whatever. G is going to be the metric on this Riemann surface times M4. And what happens is that when you look at this, it's going to be So T delta G plus JR delta D of delta G, because I picked this particular choice. And so this up to total derivatives is just the same as coupling a different stress tensor to a variation of the metric. This is called the twisted stress tensor. And so really choosing this particular background with a non-trivial R-symmetry background is the same as changing the stress tensor and then coupling the theory normally with the background metric. This is not, so what does this do? Changing T to T minus dj. If you do things right with indices, it doesn't change translation current or translation charges. It's just an improvement transformation of the current. It's just changing it by total derivatives. Charges, let's say. But rotations change. So rotations, the process for rotations is something like this, T nu rho, and the rotation in the nu plane has this current. And so this changes to, okay, schematically it's going to be something like this, where this is just an improvement. And this is the old rotation, and this is mixing it. So you mix rotations with R symmetry. So why does it help you? So it's just changing things, changing what you call rotations a little bit. And this helps you because the supersymmetries, which used to be spinors under rotations and spinors under R symmetry, they end up being, some of them end up being scalars under the new symmetry, the new twisted rotations. So among these Q's, whatever, the supercharges, let's say, supercharges. Actually, let's do specifically the case of going from 6D to 4D.
This also changes scale dimensions of the fields, right?
Yes.
And it's not a problem.
You're trying to extract an interesting 4D theory from the 6D theory. So as a side effect, you...
How can you modify the theory because you need to modify the path integral because now you integrate a different measure, right?
Well, you're putting your 6D theory on a non-trivial background, and you can choose your background whichever way you want. It's just...
It's still conformal invariant. It doesn't, I mean...
Yeah, it doesn't break conformal invariance, I think.
I mean, this definition certainly changes the scale dimensions, that's obvious, but probably it changes in a controllable way. I don't know. Ask him. Probably you redefine somehow also. I mean, sometimes you have to couple to the curvature. I know, like add to the dilaton term or something like this.
Yes, I don't know how much it changes the scaling dimension, to be honest, because.
I didn't mean to interrupt you.
Okay, I think it depends. You would have to look carefully at what is, like here I'm being sloppy with indices. If you are more careful, you have a bunch of antisymmetrization and so on, which maybe cancels out in the scaling dimension. So this, I'm not totally sure. So let's specifically do this case of going from 6D to 4D times 2D so that I can really say, okay, here are the supercharges, here is what happens. So what happens is you write R. Okay, you split R15 into two pieces, so the rotations split into those in 4D and the rotations in 2D. And the R symmetries split, you also do a similar split for R symmetries. Sorry. Where you take SO5R and you separate it, you focus on two sub algebras of it. And then what we're doing is saying, okay, I don't want to couple this set of rotations to the non-trivial metric, but I want to couple the diagonal part. But really, when you have SO2 times SO2 and you pick out the diagonal part, then you also have the anti-diagonal part, which remains. And let me call it just U1R to distinguish it from the old one. So eventually, I'm just relabeling symmetries. This is just a subset of all the older symmetries. And then I turn on a background for that. By which I mean take this T twisted and couple it to the metric. So what happens to the supercharges? Well, what happens is that you have supercharges, the set of supercharges you have is Q alpha A, where this guy is a spinner of SO13, left-handed, let's say. A is a spinner of SO3R. Then you have Z alpha A, which has the same indices plus an SO2 twist charge, let's say +1. And then you have Q bar alpha dot A and Q bar Z bar alpha dot A, where alpha dot is the other spinner of SO13, and this has SO2 twist charge -1. So these two, these Q and Q bar without index Z, they're just scalars under the two-dimensional symmetries. So they commute with the stress tensor, essentially. So you have to be a bit more careful to really see that they commute with the stress tensor. And so coupling the stress tensor to the metric is not going to break them. Whereas the other ones get broken by this, by turning on a non-trivial metric on the Riemann surface. So eventually what you find is, oops. What you find is that the theory on the 6D theory on a Riemann surface times a 4 manifold, or like times, let's do Minkowski for now, R13, preserves Q alpha A and Q bar alpha dot A, regardless of what metric you put on your Riemann surface. And these build up 4D n equals 2 Poincaré supersymmetry.
N equals 2.
I'm a bit lost at this point because, so first we started with the 6D.
Yep.
And then you went to 5D.
Yes.
And then you tried to think about the codimension too.
Yeah.
And then 4D.
Yeah, so I first said stuff about the 6D theory, and the way to access it is through a particular reduction, which is 5D.
Yeah,
But really the main object is the 6D theory.
I see.
And now I'm trying to use this 6D theory to build interesting 4D theories, which requires me to put the 6D theory on, to reduce it on some two-dimensional surface. Of course, I could use a torus, for example. I could just say, okay, let's go back to first to 5D by reducing on a circle and use the 5D theory on a circle.
Yeah.
This gives you basically 4D equals 4 super mills.
Yeah.
There are some essentially. But that's it. And I want more 4D theories. So I have to take this whole 6D theory, put it on, for example, I could put it on a multi-handled torus on a heterogeneous Riemann surface, thanks to this twist. If I didn't do this twist, I would just get some 4D theory that I have no control over. By doing this twist, I preserve some supersymmetry, and so I have a lot of tools to say stuff about this 4D theory.
But is the statement that no matter what 6D theory you start with as long as the Lie algebra is simply laced, you can always do this?
So the statement is if you have a 6D 2,0 theory, regardless of how you got it,
Yeah.
you can do that. The thing is, nobody knows any other 6D 2,0 theory other than the ones associated to simply laced Lie algebras. But it's, actually, the problem is the same in 4D, where nobody knows if there are some secret 4D equals 4 theories that are not like the standard super Yang mills. It would be extremely surprising, but it's not known. So you could imagine that someone comes up with a new 6D2.0 theory, but it's very unlikely. This twist works regardless of how you got it. And you would get 40 theories from that. There is some similar story when you have less supersymmetry. And you start from 6D1,0, and you get 40 equals 1 thing. And there you have a whole zoo of interesting things to say. Yes?
To understand correctly, that it is another twist which leads to adding some masses to this theory, so that it is not n equals 4 and but n equals 2. But in principle, there is another twist of this kind which involves supersymmetry and this SO13 remaining.
You can reduce differently. So so here I'm talking about the 4D 2D correspondence, where you do something almost topological, let's say, on the 2D side, and have a lot of rigidity on the 4D side. But you can also do a 3D correspondence, where you do a slightly different twist to make it as topological as possible on one of the factors, 3 factors, and have something pretty rigid on the other 3D factor. Or you can go one step further, and people have done, like, starting from a 6D theory, reducing it with a twist on a 4-dimensional factor. And then that defines interesting 2D supersymmetric gauge theories associated almost topologically, or I forget if it's completely topological or not, to 4D manifolds. So it's like new topological invariance, if you want, to a 4D manifold.
No, I'm asking more on addiction. So is it correct that this C2 is a kind of Seiberg-Witten curve? So this curve encodes mass.
We'll get to the Seiberg-Witten curve very soon, but it's not quite the Seiberg-Witten curve.
What
it's
is
covering it.
It's what, sorry? It's covering. Yeah. I'll get to that. Hopefully, if I speed up a little bit, then don't get myself confused too much. So the main thing is just to say, if I have a 6D theory, I can reduce it to 4D. And that's just, in some sense, I'm done saying, okay, here is a zoo of 4D theories, very abstractly defined as saying, yeah, you pick a Riemann surface, you reduce. But of course, I need to be much more concrete. And so, in order to be more concrete, I need to talk about the Coulomb branch of this system. So just like I look at vacua of the 6D theory, I can look at vacua of this 4D n equals 2 system. So the theory, which I will call TG of the surface. And there are actually also Higgs branches and so on. I'm going to focus on Coulomb branches, which are parametrized. So these are vacua parametrized by VEVs, vacuum expectation values of operators killed by Q bar alpha dot A. So they're Carroll operators. And if you look at the scalar phi, remember we had phi 1, 2, 3, 4, 5, which transformed in the vector representation of SO5. It splits into those that transform into SO2 and those that don't. And so it splits into phi 1 plus I phi 2, which I'm going to call phi z. And then, so these are phi 1 plus and minus I phi 2 have charge under under the SO2, so they end up being charged under the rotation symmetry. So they're not scalars in the twisted version of the theory. And then you have 3, 4, 5. And what happens is, if you look at representation theory, this is just like how do supercharges act on phi and so on, you discover that Q bar alpha dot A acting on phi z vanishes. Just from looking at the charges under the various SO2 and so on, you see that there's nothing that it can be equal to. So the Coulomb branch is going to be parametrized. Let's call it just CB, Coulomb branch, is going to be parameterized by the gauge invariance but by vacuum expectation values of gauge invariance built from phi z. And so if I focus just on Sn for definiteness, we know very well how to make a gauge invariant out of some phi, which is the joint scalar. We just take traces. So these are going to be expectation values of traces of phi z to the k for k equals 2 to n. So these, what are they? They are vacuum expectation values. You want to look at vacua, which are Poincaré invariant in 4D. You're looking at vacua of the 4D theory. And supersymmetry forces, so let's call it, let's call it phi k. Supersymmetry forces phi k to be homomorphic on C. So this is the expectation value of this operator at a particular point in the 6D spacetime, which is C2 and N4. And so in principle, it could depend on all 6 coordinates, but the 4 coordinates here are the dependence is eliminated by Poincaré invariance, and the anti-holomorphic dependence is eliminated by supersymmetry, essentially because dz bar of phi k, it can be written as an anti-commutator of these supercharges with some other q, and this kills the operator basically. So altogether, the Coulomb branch of the 4D equals 2 theory, well, of the 4D equals 2 theory, which is Tg of C, is the set of sections phi 2 to phi k, which are homomorphic on the Riemann surface C, and they're actually, oops, sorry, this is phi k for k going from 2 to n, which are homomorphic k, 0 forms on C. Why are they forms? Because this phi z was not a scalar. It's actually transforming under this SO2R, so it's transforming under this SO2 twist as dz, as just one form. Or rather, phi z dz. Maybe it's better to write it like this. So these are k, 0 forms on the Riemann surface. Yes?
Maybe there's like k differentials, because a k form would be antisymmetric. Or
You're right.
sorry.
Completely right. Sorry. Okay, so this is a well clearly defined thing. When C has no punctures, when it's just a genus G Riemann surface, you know what it is. Just a bunch of differential forms, not differential forms, right? And I'm losing all the erasers. And so this is the Coulomb branch. This is describing the set of vacua of your 4D theory. And then once you have this set of vacua, you can ask, what are fluctuations around these vacua? And the answer is given by the Seibel-Witten curve. Of this Tg. So the reason we're doing all this is that in principle you take your 6D theory, you reduce it, you have no idea whatsoever what the 4D theory is, and you're trying to identify with this 4D theory. and connect it to 40 theories that people had understood before. And the Seiberg-Witten curve is going to be very useful. So what is it? What is this curve? It's supposed to describe what is the, at a given point on the Coulomb branch, it's supposed to describe what is the set of massive excitations. What is the IR effective theory around this particular vacuum of your theory? So the way you do that is to remember what was phi z. Originally, I introduced it as positions of M5 branes. Now it's positions that can depend. I mean, originally it was just like constant values when I talked about vacua of the 6D theory. But now we've compactified, and now the phi's are allowed to fluctuate, and that we ended up with some phi's which we're allowed to depend holomorphically on z, essentially. And so, morally, this is, I have to put it in quotes, is the positions of M5 branes, transverse to the curve C. Now this is in quotes because phi z is not a bunch of scalars, it lives in SUN, so it's really the eigenvalues that are going to be coefficients. And this guy is not gauge invariant, so it's not so clear how you should do this. And the way you do this is to define a curve sigma which lives in T star of C, the cotangent bundle of C, and it's the set of points, so Z is going to be in C, and X is going to be in so it's the set of points such that the determinant of X dz minus phi z dz, the expectation value is 0. So here you can recognize, if you forget about the dz's, I'm just looking at eigenvalues of this matrix phi z, but I'm not allowed to take eigenvalues of phi z because phi z is fluctuating. I mean, it's an operator, it's not gauge invariant, whatever. So I look at the expectation value, and really this can be decomposed. If I look at this determinant of some x minus phi z dz, this is really this is, I forgot to put identity here. So this, you have to put the identity matrix of SUN. This is completely standard when you look at eigenvalues of some SUN matrix. So here again, identity in SUN. This is going to be x to the n minus trace phi z squared. Oops, sorry, I forgot to put that here. X to the n minus 2 minus dot dot dot. So this is really, these guys, this is just phi 2, phi 3, and so on, up to some mixing between the phi's. So really this is a well-defined object. Even though it's written like this, it looks a bit iffy. What it really means is this kind of equation, which is built from gauge invariant objects, all of whom are just holomorphic K differentials. And so once you have this, so this is, I should say, an n-fold cover of the Riemann surface C. What does it value?
Can you say why it is x n minus 2 again? Or maybe
I'm looking at traceless matrices, so trace phi would be 0.
Actually, 1/2 of on this trace.
Again?
It is 1/2.
Maybe 1/2. Yes. That reminds me. Is correct. I'm being a bit sloppy there. Sorry. So what you can imagine visually is, okay, you have a bunch of sheets on top of C. This is sigma, multi-sheeted, and this is living in T star C, and this is really describing the positions of M5 branes at a given point on the Coulomb branch. So you start out with parallel M5 branes, all coinciding. This is the CFT point, if you want, of your system. And then as you move to a specific vacuum, the branes separate out in this way. And if you want to look at massive particles, roughly speaking, they're going to be described by M2 branes stretching between the sheets of the M5 brane. And so the intuition from M theory is that massive particles, BPS particles, have masses, or I should say central charges, or have, let's say, masses equal absolute value of central charge, but central charge equals this integral, this area of this M2 brane, in a complex sense, over some disk. Which is the same as integrating over the boundary of the disk x dz. So this is the x coordinate, this is the z coordinate, dx dz is the area, the volume element, if you want, the area element, and computing the size of the M2 brane, that's times the tension, is equivalent to just integrating over the boundary, which lives inside sigma. And this is precisely the prescription. So this is precisely the prescription of how to extract BPS masses from the BPS spectrum from the Zyberg-Witten curve in 14=2 theories. So I built this thinking of positions of M5 branes and so on, but really it coincides, it captures the spectrum of BPS of massive particles in the same way as the Zyberg-Witten curve. So from that we can guess or conclude that sigma and with the differential x dz is the Zyberg-Witten curve of this 40 theory TG of C, which will allow us to to figure out what are all these theories for different Riemann surfaces. Okay, there was a story about the BPS CFT correspondence, which I have to skip. It's a generalization of AGC. That's well, not generalization. It's a sort of extension of some parts of it. But now we are equipped to talk about the basic AGT dictionary, and then I will have to stop. So here we have, from a given Riemann surface, we have everything we might want to know about the 4D theory. But to be more concrete, if you give me a Riemann surface, let's say a 4-punctured sphere, I can look at one particular limit, and I can start changing it. Oh, one thing I forgot to say is all these data, this Coulomb branch, Zyberg-Witten curve, and so on, only depend on the complex structure of the Riemann surface C. I'm talking about holomorphic differentials and so on. Everything only depends on the complex structure of the Riemann surface. This is a way to see that probably the 4D theory also only depends on the complex structure. In principle, the better way of saying it would be to say, okay, the stress tensor I got from twisting and so on is can be expressed as the supercharge Q acting on something, and then I can really prove that nothing can depend on the anti-holomorphic part. But this has, as far as I know, there's no like completely robust proof of this fact. So this is the best I can do, which is look at various IR behaviors of the 4D theory and discover that nothing depends. Everything can be expressed in terms of the complex structure of the Riemann surface. So once you have this idea that it only depends on the complex structure, you can look at a Riemann surface and stretch it very widely. So you have like 0, Z, 1, infinity, the complex structure Z. And here you have a tube that has some radius in one direction, radius in the other direction, and you have a relation of the form R4 over R5 is basically is it log Q, log Z, I guess. I'm going to ignore twisting, which is also easy to include, but in view of time, it's better to skip. So how would you describe this? Well, you have modes of the branes fluctuating, or the 6D theory fluctuating in this area, and those fluctuating here, and something happening in the middle. But in the middle, you have a very long tube. So a very long tube should make you think of S1 times, okay, some interval. And the 6D theory on that should be the same as the 5D n equals 2 squaring mills on this interval. 5D n equals 2 squaring mills has this type of term in its action. And when you take this and integrate, so this is a 5-dimensional integral, you can split it as a 4-dimensional integral and an integral over the interval. And so this should give you, at least if the fields don't fluctuate too much in there, it's quite reasonable to hope that it should give you this kind of term in the 4D action. So here you have a 4D Yang-Mills term. The 1 over R5 came from the identification of 5D gauge coupling to R5, and the R4 is just the integral over the length of the interval. And so this is like 1 over the 4D gauge coupling squared. So basically, by knowing that the 6D theory reduced on a circle is 5D equals 2 squaring mills, and then integrating this term on a long interval, you can guess that the effect of such a tube should be related to 4D squaring mills with a gauge coupling that is related quite simply to the shape of the tube. So concretely, the dictionary that comes out of this consideration is that if you only understand T of some Riemann surface, whatever, some complicated Riemann surface with a certain puncture with local coordinates that I'm going to call Z1, close to this puncture, and you already understand the same for a different Riemann surface, Z2, then you can glue them by somehow adding. So you can look at the TG of the combined Riemann surface with the identification Z1, Z2 equals some complex parameter Q. Well, this is going to be the two theories plus some gauge fields, some 4D n equals 2 super mills, so vector multiplet with coupling 1 over g squared given by log of q, which is the gluing parameter here. So this idea requires you to, so this is gauging flavor symmetries of the theory. So you need, for this to make any kind of sense, you need these theories to come equipped with a flavor symmetry. So you need punctures that are called Z1 and Z2 here to come with, to carry, let's say, flavor symmetries. The other thing that you can extract from this is going the other way around. What type of punctures are the most important in this construction? Like what if you start from such a Riemann surface and you pull it apart, how are, for example, phi 2, phi 3 that I defined, how are these differentials going to behave in this detached limit. And so that is going to tell you what punctures you have. And then I will stop. If I find a chalk. So if I look at a differential, a K form, no, not K form, sorry, a K0 differential on the tube, on the long tube, it's going to go to some limit in the middle. So if I have S1 times R, and I want to have a coordinate that looks like this, and I want to work in the coordinates W equals log Z, which maps Z living in some sphere to, okay, this is harder to justify than I remembered. So the rigorous way of saying what I'm trying to say is, you look at typical phi2 differential, like 2,0 differential on this thing, and you send z to 0, and you look at how it behaves in the middle, and what you will find is that in the middle, phi2 behaves like, has a second order pole. So, so the reason I want to go to this coordinate was, you can also understand as just dw squared. So by correctly taking the limit, you get the following very concrete thing, which is that this non-gauge invariant thing I was mentioning, near a puncture, it will go to some finite limit, some matrix M, dz over z minus, well, the position of your puncture. So this you get really by just taking concrete phi2, phi3, phi k, and stretching, like taking the limit in which one of the tubes becomes very long, and looking at how these differentials want to behave. And the answer is that these differentials, which are order k in this thing, want to behave as some coefficients, some constant, times dzk over z minus z star k. This is going to be the starting point of all the analysis of all the various punctures you can build. And then once you have these punctures, you can understand really the whole dictionary of AGT. And this is for next time.
All right. That's time to
Thanks again. So just as a reminder, yesterday we saw that there is this relation between 2D CFT and four-dimensional gauge theories, and we saw the origin from a certain six-dimensional SCFT, supersymmetric theory, and we started seeing the basic dictionary, which is that, okay, you take this 60 2,0 SCFT, you put it on some Riemann surface, okay, using a twist. We can do the dark thing if you want, but everybody will fall asleep after skiing. Anyway, so we put it on some Riemann surface and we get some 4D n equals 2 system. And one step I forgot to say is that I shrink, well, I take the area of C2 to 0, which essentially morally reduces to 0 modes of these 6D fields. Of course, you don't have a field, this field theory description here, so it's just morally, and you eventually get an actual four-dimensional theory instead of something that is still has lots of fluctuations in the Riemann circle. So this gives you a 4D n equals 2 theory, T of C, that depends on the Riemann surface and the punctures. And we learned yesterday that Coulomb range vacua of T, let's focus just on SUN today, are labeled by meromorphic K0 differential, meromorphic differentials, differentials phi k on C for k from 2 to n. So these were traces of, essentially traces of powers of some underlying non-gauge invariant field. And we also saw that the effective field theory near such a vacuum is described, is controlled by the Zeiger-Britton curve. Which is the set of solutions to such an equation inside the cotangent bundle of C, which is a rigorous, correct way of defining the non-gauge, like not quite gauge invariant equation, which I'm writing here, which is that where phi z was this matrix, this element of SUN that described that is morally homomorphic and this, on C and describes positions of M5 rays. This is not a really precise object, but still it's good to get some intuition of what type of behaviors we should expect for phi k. And so now we're getting to new, not quite new stuff. Sorry, I have to say one more thing. We also saw that if you want to understand the theory associated to a Riemann surface C1, which you glue to a Riemann surface C2 through a puncture of C1 and C2, that this is the same as taking the theory for C1, the theory for C2. These are just collections of fields in 4 dimensions, so you just put them on top of each other on the same 4D space, and you gauge a diagonal flavor symmetry shared, well, the diagonal subgroup of a flavor symmetry of this theory and a flavor symmetry of the other theory. And so this thing, yes.
Is there a dimension problem? Like, isn't it xdz square? And I mean, if it's inside the T star C, then it should be quadratic differentials, right?
This equation is homogeneous of degree n. It should be. This is a k0 form. This is an n minus k0 form. So total is n0 form.
But why is it
n solutions?
Why should it be of degree 2?
Differentials? Thank you. Sorry.
If it's in T star C, why isn't it of degree 2?
No, T star C is 1 forms on.
Yes.
It's like one 0 forms on C.
Yes, but so dz to the n is. Okay, maybe it's my problem.
So this is a degree n polynomial in X, if you want. And so you just find solutions which have the form X. So really it's the set of X dz such that...
So isn't dz outside of the bracket? Because dz to the n is an n differential, no?
This is an n differential. This is a degree n equation in the variable x dz, if you want. Which is a 1-0 differential. well, in this case, a form.
Okay.
Okay, but it's
yeah.
not going to be absolutely essential.
Yeah, no, it's just.
We should maybe go to the next time. So in order to make a precise sense of this, we need to understand what are these flavor symmetries, which are associated in some sense to the punctures. And so we need to understand punctures. So the easiest way of saying what punctures are is to say that this non-gauge invariant field, phi z, blows up at puncture. So you just describe its behavior as a certain constant SUN matrix M. So let's say you have a puncture at a certain point z star. You write it like this, plus order of 1 terms. So this is a prescribed behavior near a particular point z equals z star. And what this translates to in a gauge invariant way is phi k, which is combinations of this of degree k, will have a certain behavior as dz to the k over z minus z star k plus some lower order terms, which are in 1 over z minus z star to the k minus 1 dz k. So these are k0 forms, k0 differentials, sorry, that are holomorphic in Z, and we're prescribing a particular blow-up where sigma k is built from the eigenvalues of that. So this is a way of describing, in a gauge invariant way, what is a puncture. So instead of saying generally we take meromorphic differentials without really saying what's happening at the punctures, we say, okay, they blow up in this particular way. Now, in order to so this is called a full puncture, a full regular puncture. And as a spoiler, this is going to correspond to vertex operators, usual vertex operators of the Toda field theory, inserted at this point z star. And the parameters here are going to be in one-to-one correspondence with the momentum in Liouville or Toda field theory. Now, there is actually a whole zoo of punctures, and one way of understanding them is to go to the massless limit. I should say that eigenvalues of M, I mean, this guy is mass dimension 1, so M has mass dimension 1 in a 4-dimensional space. And so the massless limit is when you send the eigenvalues of M to 0. And what happens then is that sigma k, which were just various polynomials, symmetric polynomials of these eigenvalues, these also go to 0. And so the limit of this full puncture is going to just be a prescribed, an allowed blow up of order k minus 1 for each differential k. This is a full massless puncture. Yes?
I'm slightly lost. Can you explain what happened there?
Which side?
Yeah, from there. So it's like, yeah, how do you know what it looks like?
This is the simplest, the least singular blow-up that you can have. That is not a branch, that doesn't have branch cuts or anything. And you can also play games with branch cuts, but that's much more complicated because then you have to end it somewhere else, and then it's really a line operator in your Riemann surface. I just want local things, so local prescribed behavior. If I was really doing field theory in 6 dimensions, I would really just say I change my path integral. Instead of integrating over phi, a scalar field that is smooth everywhere, I integrate over scalar fields that have a very specific blow-up near z equals z star. Here I cannot really say that because I don't have a field theory description of the 6D theory, so I have to say, okay, this phi is not really well defined, it's only only the gauge invariant things in 4 dimensions are really well defined.
And it is constant in the transverse directions, right? It just, I mean...
Yeah, all this is constant in the 4 space-time directions. So yeah, this is just a prescribed behavior at one point in the Riemann surface times R to the R4.
And just take it by definition. Just consider the effects of this type. That's
Yes,
it.
yes.
Don't care where it comes from, just by definition.
Yes.
Uh-huh.
Although, of course, it's like you really just juggle between various different descriptions of the system,
Yeah.
and none of them is fully well defined until you really get to, here is a four-dimensional theory, I know what it is, I have a Lagrange description, I have everything to know what I'm talking about. So here I can only say, okay, morally you have this non-gauge invariant thing, it leads you to this description of the set of vacua of the system, but just knowing the vacua is not enough, so it's not...
I think my question, the thing that is really surprising me a little is the massless limit and why those can be seen as masses. The spectrum of M.
So M is the dimension of mass.
Yeah, so the M, this matrix has dimension of mass, and so trace of M squared, for example, is a mass squared, trace of M cubed is a mass cubed, and so all these sigma k, for example, which are basically traces of M to the k, not quite, but they're just going to be of mass dimension k, and so if I want to take the massless limit, I just send all those massive, like, dimensionful parameters, to 0. But I'm still left with the allowance of having such a singularity, so there is still something non-trivial going on. One way of seeing this is to think of it as being the case where M has a bunch of zeros, but then, I mean, matrices with spectrum 0 are not necessarily trivial. You have all the nilpotent matrices. And so this would be the full puncture okay, I guess I should probably write it here. So this full massless puncture corresponds to M equals this maximum nilpotent matrix. Now you have a classification of these massless punctures, which can also be done in the massive case, but the dictionary is not so immediate, which tells you then that different defects, different types of punctures, are labeled by nilpotent orbits of SLN, which is the same as partitions of N. And so the case that I'm interested, the second case that I really will need is the case of simple punctures, which is the other extreme, which is M, which is now minimal, just a bunch of zeros everywhere, except a single one. And then when you track what it means for the various, this determinant of x minus phi z, you expand it to get the phi k. What you learn is that phi k, now instead of having the right to blow up to this order, is only allowed a smaller first order blow up. So this is a reduction of these full punctures. And you can really track more precisely what is this reduction from the gauge theory point of view. It's some kind of Higgsing, but time doesn't allow me to go through nitty-gritty details. The main thing is I will need these two types of punctures to move forward.
Only this, or you will allow another route of
Apologize?
only this simple route, or you will allow any simple route of the, I mean, do you allow like...
This is for all k. So
no, I mean the matrix M, simple function, it could be only of this way, or this can be...
Only of this way. I mean, you have all possible partitions of n, but I'm only going to care about the partition that's just 1 to the n, oops, sorry, 1 to the n, the full puncture, and n minus 1 n, sorry, n minus 1 1, which is this simple puncture.
This corresponds to
This is
the first fundamental wave.
Yes. Yes. Okay. So you have these punctures, and using these, you can now make lots of concrete Lagrangian examples of these theories. And so the thing is, let's first tell you a bit about SU2 case. T of any Riemann surface. So in the SU2 case, you have only a single type of, like all punctures are full. Because 2 has only a single non-trivial partition, So all punctures are just full. And so if I take a random Riemann surface, I can just say that this is a bunch of 3 punctured spheres glued together. So you have like 2g minus whatever plus n. I don't know if the number is completely correct, but then you gauge symmetry. One thing I forgot to say, sorry, is these punctures had n mass parameters, these 4 punctures, and they carry SU1 flavor symmetry, which means that, I mean, in the sense that you can turn on a background field, and turning on a mass, going back to the massive case, is equivalent to turning on background value for a vector multiplet, gauging this SUN flavor symmetry. You really have a duality between the set of mass parameters you have, not the duality, I mean the direct correspondence between the set of masses and the type of flavor symmetries that the puncture carries, that the puncture gives to the 4-dimensional theory. And here, in the same way, you can track that this has only 1 mass parameter, and so this gives you a U1 flavor symmetry for n greater than. In the SU2 case, all punctures are full, and everything reduces to just this theory gauge. And what you can do is look at the Coulomb branch, just focus on this theory. The Coulomb branch is just a point, and the Zyberg-Gutsen curve is whatever it is. I mean, it's a double cover of this thing with the branch cuts somewhere, and you can check by looking at the BBS spectrum of these things that this is exactly matches free hypermultiplets. So this is just free fields with a very specific, very well-known Lagrangian and so on. Well, I should say half hyper in the tri-fundamental, so the tensor product of 3 fundamental representation of SU cubed. And this allows you to say a lot of things about.
Sorry, Bruno. Did you say what G and N are?
What?
G and N.
G.
G is the genus.
It's the genus of this thing, and N is the number of punctures. Sorry, I didn't say, but it's just some number of pairs of pants. I have no idea what this number should be. It should probably be like less precise. But it's a very easy topology. So the point is, if you give me, okay, let me remove this view. If you give me this, then I can really directly give you a Lagrangian description of this theory by saying, okay, I have a bunch, like I cut here to get pairs of pants. So I have 2 SU2 gauge groups. And each pair of pants is a bunch of hypermultiplets. And if you work out the precise number of hypermultiplets, you discover that this is, okay, I want to say 2, but 3. This is an SO4. So 2 SU2 flavor symmetries, 2 SU2 flavor symmetries. And this also carries an SU2 flavor symmetry. So this notation is just saying you have a bunch of gauge fields, so SU2 gauge fields, and then here some matter fields, some free hypermultiplets that are, whose symmetries are gauged by these gauge fields. This is a very explicit Lagrangian, you could write it down, and this is known as SQCD with NF, so SU2 SQCD in 4 dimensions with NF equals 4, and we saw this theory show up in the last talk this morning as one example of theory for which we know how to compute various things.
So this is for a specific C or what?
This is for this specific 5-punctured sphere. If you had more punctures, you would have more gauge groups here. A longer quiver gauge theory. This is called the quiver gauge theory. And if you had holes, so maybe this is another example I should give. If you have a torus with 1 puncture, you can cut it as well. Cut it somewhere. And then this is going to be, this has 1 SU2 gauge group. And SU2 is gauging 2 flavor symmetries of the same set of hypermultiplets. And so what happens is, it's in the fundamental tensor, the anti-fundamental, so it's actually an adjoint hypermultiplet. And this is the theory called n equals 2 star, which also showed up this morning.
And can you explain the meaning of the word matches? What does it mean?
Matches the Coulomb branch and the Seiberg-Witten curve that you get from the 6D abstract considerations are exactly those that people derived from looking at the spectrum of these theories. Well, in this case, it's just free hypermultiplets, so it's just something you can really write down what is the set of massive excitations. They're just going to be sums of the various mass parameters, just the mass parameters that you have in your Lagrangian. Here, this is work by Seiberg and Witten to take this SQCD theory and understand that various consistency conditions give you access to the low energy description of this theory at a particular vacuum in the Coulomb branch. So everything matches in the sense the 6D story matches with previously known 4D stories. And in fact, it's basically this matching that's told, for example, Gaiotto and collaborators that they had the right matching of parameters and so on. So this is the SU2 case. In the SUN case, the situation is much worse because...
Yeah, but the theory doesn't... I'm sorry, I interrupted.
But there are two gauge groups there.
in which case? In the torus case? Or?
So you said that is SU...
Oh, yes. I was planning to only have a 4-punctured sphere.
Yeah.
Correct. So if you have a 4-punctured sphere, then you have only a single gauge group, then it's... Sorry, I said something completely wrong. Sorry about that. So SQCD is the one with only a single gauge group. Sorry. I mean, this other one was also studied before, so it's not like Gaiotto and company discovered anything. This discovered new 4D physics, but it was a nice check of the dictionary. This is NF equals 4, SU2, SQCD. I should say 4D equals 2. Okay, so this statement is actually correct, sorry. This one is some more complicated here. Thank you very much. So for bigger n, I cannot get away with putting all the punctures to be the same. So if I try to tell you, okay, let's pick a random surface, let's do the same, but now the punctures are punctures of SUN, so here it should say SU2 all over the place. Then you have to tell me, I have to figure out what is this theory here. And so the question becomes, okay, if I have 3 full punctures, so this is 1 to the n, 1 to the n, 1 to the n, 3 full punctures, what is it?
3 full punctures or 3 simple punctures?
3 full punctures. 1 to the n was the full puncture case.
Yes.
If I have 3 full punctures, then this should have no gauge coupling, because a 3-punctured sphere has no continuous no complex structure. But it should have SUN cubed flavor symmetry. And it should still have a Coulomb branch. You can check that. So it's not just a point, it's more complicated, because when you look at differentials, phi 2 that blows up in a certain way, phi 3 that blows up in a certain way at these 3 points, and so on, you find that there are some extra parameters available. And so in the end, you find that there's no Lagrangian theory that fits the bill. Lagrangian theory. So you just give it a name, you just call it Tn. And you can study various properties of it, but really there is no direct construction of it. There is a 5D construction, which I can tell you about separately, but it's to go from the 5D description to the 4D, it's a bit complicated, and you really don't have, it doesn't give you a very good handle on the 4D theory. So instead, what you're going to do is restrict yourself to a simpler set of three-point function of three-punctured spheres, which are with a simple puncture here. So simple and full and full. And now you only want SUN times SUN times U1. For symmetry, you can check that because the pole is of lower order, you actually don't have, the Coulomb branch becomes just a point, and you can really look at the error description and so on, and everything is very simple. And this ends up being n squared free hypermultiplets, which are in the fundamental, tensor anti-fundamental, tensor whatever, charge 1 representation of these three flavor symmetries. And from these, you can build a lot of interesting Lagrangian theories. Sorry. So what we can build, for example, is for the four-punctured sphere, which are going to be my... Okay, can someone remind me what the usual symbol for full and simple and so on punctures are? I know there is some convention, but maybe Jörg, you remember. Okay, let's pick a convention. Like this is a full puncture, and maybe this is a simple puncture. Maybe it should be the other way around, I don't know. Full, simple, simple, and cut. And this is really the gluing of two such things. And what you find is you have a single gauge group, SUN. You have two sets of hypers. Here it's n squared hypers. I mean, in total it's n squared, but it's like n times the fundamental representation of SUN, n times the anti-fundamental of SUN, but this is really equivalent when you have such hypermultiplets. And so at the end, this is SUN SQCD with NF equals 2. And just like before, you also have the similar story on the torus, where now you have a simple puncture, which is going to be SUN with an adjoint hypermultiplet, which is called n equals 2 star. It's a deformation, it's a mass deformation of 4D n equals 4 superannuals. So you have all those nice theories, and you can also make quivers in this way. Okay, fine. What do we learn from all this? So one thing we learn is, okay, you can make very long quivers, and then you can extract Coulomb branches, and Seiberg-Witten curves are very long quivers, which were sort of known before, but this gives you another way of reaching them. But the more important thing is going to be looking at observables and making contact with Liouville and TODA CFT. So, I'm talking about 4D theory so far, and I'm now going to look at another specific observable, which is the ellipsoid partition function of this 4D theory. What do I mean? Well, what will I get is a better question. I will get that the partition function on this space, which I will describe shortly, of this four-dimensional theory is going to be equal to something you can compute just from the Riemann surface, which is a 2D TODA CFT. Well, I guess there is a dependence on G, correlator on the Riemann surface C with all its points. So to make sense of this, I have to explain what is this, how to compute the partition function, and what is the TODA CFT. And once we have that, we will have a matching between various objects of the 4D on the 4D side and concrete building blocks of TODA CFT, all the vertex operators, conformal blocks, and so on. Okay, so there's a very long story of how you put a QFT on curve space. I mentioned a little bit earlier, yesterday, how to do it. You have to turn on a metric, so you have to deform the Lagrangian by some metric, and also turn on all sorts of other background fields. And you want to do it in a way that preserves isometries and preserves some supersymmetry. So if you only care about preserving isometries, you want scaling vectors. So isometries are equivalent to having killing vectors, having some, I don't know, y, such that nabla y plus nabla y exchange equals 0. This is a killing vector. And likewise, if you want to preserve supersymmetry, you have to make sure that all your background fields and so on, not just your metric, but also the others, give you what are called generalized killing spares. And I don't want to go in too much detail because it gets quite messy. But the main thing is Hama and Hosomichi. Oh, I guess I said I wouldn't cite anyone. You can just look at my review. So they built, so H and H, built a supergravity background, S4b, which you can think of as I mean, it is a squashed sphere, squashed version of S4, which you can think of as being embedded in R5, which has a squashing parameter B, which is the same as the B of Liouville, the same as B of Toda, and so on. Inside R5, and they have, so this is just giving you the metric as embedded surface, hypersurface inside R5, but you also have to worry about all the other fields, and this background preserves a supercharged Q, where Q squared is an isometry, which consists of rotations in the 1-2 plane and R symmetries. The carton of SO3R, we had this SO3R symmetry earlier. And then you have a second piece, which is rotations in the 3-4 plane as well. So this is, the main thing to see is that there are these rotation generators that leave this S4B invariant. And this is a rotation around a sphere, which I'm going to call S2B. And the other one is around a sphere which I'm going to call S2 1 over B, which are two different loci where interesting things happen, which are fixed points, if you want, of fixed loci of this Q squared rotation generator. So the sort of magic step that I'm not being historically accurate in the order in which I'm presenting things, because it would force me to say, okay, first we talk about S4, not squashed, it corresponds to B equals 1, and then we say, okay, people did all those calculations, then these guys came up with this background which is squashed, and they redid the calculations and so on. So I'm just going to give more directly how the results work. But still I want to cite Pestun in 2007, who started the whole field of supersymmetric localization applied to non-topological field theories. So this, I mean, it applied to physically interesting theories, to exaggerate a little bit. I mean, supersymmetric localization existed before, but it was not nearly as useful. So what is this? It applies to Lagrangian theories. So it will not tell you anything about these Tn theories or more like high point spheres where you have only full punctures. It will tell you a lot about these theories. And the idea is you pick functional, which is roughly of this form. You have this supercharged Q, that's this one. And you pick a functional that's morally of this form. where you sum over all fermions in your theory, so both the fermions in the hypermultiplet, so the squarks, I should say, and the gaugino in the vector multiplet, you sum over all of them, an expression of this kind. Dagger is some notion of conjugation, which is not so important for what I'm doing. I mean, you have to work out very carefully what it is. And then the key is that so the partition function is just, the partition function you care about is just the integral of e to the minus s with a measure. And what we're going to do is to introduce a parameter t, which t is just a real number, positive real number, and we're going to deform the action by qv. And this, okay, I just need a notation for the measure. This is t independent. Why? Because if you take a t derivative, what happens is dt of zt is going to be this integral e to the minus s minus t qv, and you can integrate by parts and make q act on everything else. We have different terms for each piece. The measure is q invariant. The action is q invariant. This qv is taken to be q invariant. So we need q squared v equals 0. And at the end, this just gives you 0. There are, of course, lots of convergence issues, but in any case, the path integral itself is not well defined for these 40 theories. So you're welcome to try and give a precise mathematical meaning to all this. I don't know how to do it. The main thing is, maybe I should stay on this side. The main thing is then z that you care about is the value at 0 is going to be equal to the limit when t goes to infinity of dt, which localizes, which is equal to, which reduces, let's say, to zeros of qv. So configurations of the fields such that this qv is 0. Because if qv, so qv is basically cube psi squared plus lambda squared, so it's something positive. If you take a configuration for which it's strictly positive, then it's going to be completely suppressed by this e to the minus t qv when t goes to infinity. So you only keep the zeros of qv. And so qv equals 0 becomes essentially cube psi squared plus q lambda squared equals 0, which are very strong sets of equations because this only vanishes when all the terms vanish. These are very constraining equations on these things. And these are bosonic equations. There are equations on the gauge fields and the scalar fields and so on. So, what that gives you is a reduction of the infinite dimensional path integral to a finite dimensional path integral. And I'm going to specialize, rather than going through the whole details of how it looks like completely generally, I'm going to specialize to a particular theory, which is, which was this thing. Well, I guess, okay. Let's write it like this. T sun of this Riemann surface, which had 2 simple punctures and 2 full punctures, which is, remember this was sun sqcd. With 2 flavors. And what happens is that this reduces to, so zeros of this cube psi and q lambda, they are parameterized by the value of a constant value. So these are very strong differential equations on the sphere for all the fields in your theory. And they force the scalar field of the vector multiplet to be constant. And so this belongs In one writing, it belongs to SUN, so just a constant value, but you can always reduce such matrix integrals to, often, to the Cartan subalgebra. So it's going to be in the Cartan of SUN. This parameterizes solutions of Q psi equals 0, Q lambda equals 0. And then for each such solution, so QV vanishes, and you have to look at the value of e to the minus s at this classical solution, so e to the minus s classical, which is going to be the gauge coupling, well, I guess Z was the gauge coupling, maybe in terms of positions of punctures it's this. So we get this gauge coupling to the a squared. This is trace a minus trace a squared. I'm taking a imaginary. There are a bunch of conventions that worry about. So this is the classical contribution, just the value of this integrand there. But you also have to worry that there is a change of, essentially a change of variable. The change of variables. Yeah, let's say that way. I mean, it's. The more precise statement is when you send t to infinity, you still have a residual effect of this coming from a Gaussian integral around this locus q psi equals 0, q lambda equals 0. And this Gaussian integral you can perform, you can compute exactly. And it's going to be so-called the one-loop determinant, which depends on all the fields that show up in QV, which are the gauge fields and matter fields. So it's going to split as the product of Z1 loop of the hypermultiplets, which I have here very explicitly. Product over the gauge field components, product over the flavors, the n plus n flavors, so 2n flavors. I think I don't want to call it I, maybe A. Epsilon is some complicated special function. So this is z hyper times z vector, which is another product of epsilons. A minus AB. These come from fluctuations of the fields in the hypermultiplet or vector multiplet around this particular element of the localization locus, so this particular solution of these equations. And this is missing a big, very important piece, which is the following. And this piece, the instant-on partition function, also essentially equal to the Nekrasov partition function up to some unimportant factors, is so this, how does it come? How does it arrive? Well, I cheated a little bit when I said the localization locus of the solution of q psi equals 0, q lambda equals 0 is just constant values for the vector multiplet scalar field. The actual localization locus is constant. Let's call it phi, the scalar field, or yeah, let's call it phi equals a. Phi is not a good notation because we did all replace. Let's call it sigma. So the vector multiplet scalar is equal to a constant value a, and well, and A mu equals 0 away from poles. And if you look carefully at the equations, they actually also allow instanton configurations. So configurations with non-trivial behavior of a. How much detail? Yeah, they allow point-like instantons at the poles. I guess it's y5 equals 1 and y5 equals -1. And so there is only a heuristic argument for what is exactly the contribution from these instantons in the localization calculation. These instantons, let's say at those at the North Pole, these are solutions of F, so the field strength of A equals star F. So self-dual instantons. And the set of solutions of this equation, the problem is there's an order of limit issue that was never resolved in the literature, so that's why I'm kind of fumbling around. When you do this localization calculation, the equations you get really only allow non-trivial solutions at the poles themselves. But it doesn't really make sense to talk about instantons at the pole itself. So what you have to do is to look more carefully at what the theory looks like near, like you find that the equations seem to allow more stuff at the pole. The field theory near the pole. And what you find is that the theory S4B near the pole looks like the omega background that Arlo mentioned this morning. So this is the omega background. So by this I mean that if you really look at the supergravity fields, so the metric and the R symmetry background and so on, near the pole you expand, you rescale everything to zoom in at the pole, you will find that this is a deformation of R4 with two equivalent parameters which were called epsilon1 and epsilon2. And then Peston guessed, and it was checked extensively afterwards, that the contribution you have to include, this contribution at the poles, should match with what Nikita Nekrasov had defined as the partition function on this omega background. Had computed as the partition function, had genuine calculation of the partition function on this omega background, where you have instantons of finite size, and you talk about the moduli space. You can really talk about the moduli space of solutions to this self-dual instanton equation in a meaningful sense. And you can study what are the set of the moduli space of solutions you can compactify, and you can really compute the volume of this moduli space. So really compute the path integral of this system for the enclosed theory on this background. Unfortunately, the precise connection has never, I think, been done in this precise context. So it's more like a conjecture that you should get the instanton partition function at the North Pole and the same at the South Pole with a different self-duality condition. This is very reminiscent of the decomposition of 4-point functions in 2D CFT into 3-point functions and control blocks. So that leads me to the link to 2D CFT. Which is that, okay, the S4 partition function that I wrote here is TODA CFT correlator, TODA CFT being a generalization of Liouville. where instead of a single scalar field, you have a scalar field in the carton of G with exponential potentials that are related to the structure of the Lie algebra G. It's sort of a single exponential potential. So the squashing parameter B is so B here is B, is the coupling constant. The gauge couplings, tau, let's say, or Z, whatever, is the complex structure. The cross ratios, if you want, of the punctures. Then you have an important aspect of toda CFT correlators is that you can do bootstrap. You can perform braiding moves, and you can change the Pence decomposition. So let me call it braiding in general. And this will correspond to different descriptions of the same theory in terms of different building blocks. So you take, for example, this. You can cut it like that, or you can cut it like putting these two punctures. Maybe I need another color. These two punctures together, and these other two punctures in the other pair of pants. And this gives you two different descriptions with different gauge couplings of the same 14 equals 2 theory in principle. And this is called S-duality. And then you have a precise dictionary of between punctures, full punctures of mass m. This goes to a vertex operator up to some normalization, which is e to the, this usual definition. We're now, this should be phi, or the scalar field of toda field theory, times some momentum, which is now q plus m. Q is a vector in this case. M is a vector. All these guys are in carton of SUN. And then you have a complete dictionary, simple punctures, correspond to momenta with which are some coefficients times the first fundamental weights. You can call it H1. So this is a special case, if you want, of this. And this is such that it has no descendants. So it's not an operator, primary operator that has all possible descendants under the generalization of Virasoro that matters here. It's an operator that has some null states in its descendants. This is deeply related to the fact that we can compute stuff on the gauge theory side and on the toda CFT side. Maybe then I have to stop this. So non-descendant. So how would you go about computing correlator? Let's say, okay, how would you go about computing such a correlator? Okay, maybe I need to be more precise about the coefficients. Let's call it kappa. Sorry. So this is a 3-point function, and the dictionary, which I could complete, tells you that this 3-point function should be related to these one-loop determinants. So it should be given by this, well, mainly this formula. So it should just be a product of epsilon functions, very concrete product of n squared epsilon functions. This is an analog of the DOZZ formula in Newville. So how do you prove this kind of result? Well, what you do is you look at a 4-point function with these 3 points plus a degenerate field. And we saw such degenerate fields in a talk yesterday. Who was it? I forget. Guillaume Barres gave a talk on these degenerate fields. These guys, he gave the Liouville story, that you have fields with null descendants under the Virasoro algebra. You have a similar story here in total CFT, where you have a bigger symmetry algebra called Wn, and these guys have lots of null Wn descendants. And this is enough to understand, to fix the monodromy as you take the position. So this is position 0, 1, infinity, and z. As you take z around 0, 1, and infinity, and more precisely, it fixes the exponents, the powers of z that you will see. It's differences of dimensions that you get. And also, so it fixes the monodromies, and it also makes the integrals over control blocks that Jörg got, so this integral of momenta and so on, into, so the integrals into sums of control blocks. Finite sums in this particular case of n control blocks. And so what you find is that this set of control blocks, which you can label by these types of diagrams with like some momentum, maybe 2, alpha 1, kappa h1, minus bh1, and here some internal momentum. That these control blocks, this is an n dimension, a set of n control blocks, which are subject to monodromies described by matrices. So the monodromies are given by 3 matrices, M0, M1, and M infinity, that are n by n, such that you know the spectrum of M0, it's related to the momentum of 2, I guess, here. M1 is related to the momentum here, M infinity, sorry, to the momentum here. And you know that M0, that if you go around all 3 punctures, you actually go back to a trivial loop, so that M0, M1, M infinity equals that entity. And this actually has a single solution. In the case where this one of the momenta is has this special structure, such that the spectrum is less general than just 3 arbitrary spectra. Since you have a single solution, you can pose a Riemann-Hilbert problem for the control blocks and solve, and you get hypergeometric functions. By looking at the expansions at various limits, that gives you very strong constraints on the 3-point functions that show up here, which are 3-point functions shifted a little bit. And that's, I was sort of hoping that Jörg would be talking about his old work on that in Liouville, but that's not happened. So anyway, this is enough to completely fix these 3-point functions on the total side. And for that, it was essential that the spectra of these matrices are not as general as possible, but they're slightly restricted for one of them. Okay, I went over time. Well, I guess I went to the normal time. But,